In chapter 2, I told you guys that you have to know how to factor and you have to know how to do quadratic formula or you are going to suffer. Okay, do you guys now see why I made such a big deal out of that? There were probably 6 different places on your test where you had to factor something. Okay, the thing for chapter 3 is exponent rules. You've got to know your exponent rules. Now, usually my students are much better at exponent rules than they are at factoring when they come in, so I didn't include that on our little tests at the beginning. But as we're going through today, especially with this first block of problems, if you find yourself not understanding some of this stuff, then you're going to want to go back and review those exponent rules, okay? Like right now, if I asked you, like, do you know when do we add exponents? Can you give me an example of a situation where we add exponents? And a situation of an example where we multiply exponents? When do we subtract exponents? And what do negative exponents mean? Those kind of things. If you need to review that, please review that. So let's just kind of test ourselves right now. Like I bet you guys can do most of these on here. At least half of them. At least half of them. What I'm asking you to do for each of these problems is rewrite it as 2 to a power. So what exponent can I put on a 2 to make it equal to 1? What exponent can I put onto anything to make it equal to 1? 0. Anything to the 0th power is 1. You guys knew that, right? If I want to make something equal to 2 and I'm starting with a base of 2, that's pretty easy. What do you put on there? 1. Yeah, you guys know this stuff. Ooh, I want the 2 to be in the bottom of my fraction. What exponent can I put on something to move it to the bottom of a fraction? -1. Okay, you guys got this. You guys got this. Now this time, I'm asking you to give me an exponent on a 2. How am I going to turn a 2 into a 4? Yeah, 2 squared is 4, but I want it on the bottom, so -2. You get the idea? Yeah. This next one always throws my students for a loop until I give them one little hint. Let me give you the little hint on this one. There's an exponent of 1 on that too. All right, so what am I going to do with that 1 and that x? My bases match. I'm multiplying 2 bases that match together. Am I going to multiply the 1 and the x, or am I going to add them? Add them. I think I'm going to do this one in 2 steps. I'm going to think of this as, I'm going to rewrite 8 as 2 to a power. 8 is 2 to the 3rd power. So 2 to the 3rd power times 2 to the x power. Again, what am I doing with my 3 and my x? Add them. Yes, it's coming back, isn't it? Do you guys remember loving these exponent rules back in Algebra 1? Did you do a lot of exponents last year in Algebra 2? A little bit? Okay, good. All right, what are we going to do here? Ooh, I'm dividing exponents. What should I do with my 2 or my x and my 1 this time around? Subtract. All right. X minus 1. What do you say on this next one? We think of this 4 as 2 squared. Huh? That would just be 2 to the x minus 2. All right, so we've replaced 4 with 2 squared a couple times here. Now, I'm going to put a 2 squared on there and then an exponent on there to lessen my confusion. I'm pulling the 4 out, and I'm going to leave a parenthesis in its place. And then I'll replace the 4 with a 2 squared. Same thing, right? What do we do with our exponents this time? We got a power inside and a power outside. Multiply them. See what you can come up with for these next couple here. How about square roots and cube roots and fifth roots? Do you guys remember how to make those into exponents? Your exponent's just going to have a fraction in it, right? Whatever the root is going to be the denominator of your fraction. So this is 2 to the first power, so this would be 2 to the first, and then the square root would be over 2. So 2 to the 1/2. 2 to the 1/3. Let me just rewrite this 8 as 2 to the 3rd. So this would be 2 to the 3/5. So when you've got an exponent and a root, those both go into your fraction. Exponent goes in the top, root goes in the bottom. And it doesn't matter whether your exponent's on the inside or the outside. Same deal. Same answer. How are we feeling? Okay. All right, and while we're talking about square roots, this isn't on here, but this is going to come up. If we're solving and we get an answer like 5 over this, the square root of 5 over the square root of 3, say, you guys know we can't leave our answer like that, right? Can't leave that square root in the bottom. What fancy version of 1 would you multiply this by so that we didn't have a square root in the bottom anymore? You'd multiply it by root 3. And you would get square root of 15 on the top and just a plain old 3 on the bottom. Do we remember rationalizing? That's going to come up every now and then too. So these things up here, we want to make sure we're good and comfortable with them. I'm introducing them now. They're not going to come up much today, but where we are going to see them is if we flip ahead. And by the way, it's really unfortunate how this packet printed. I do not know why every other page is upside down, but we're going to have to deal with it. I know, it's really annoying. So we're going to mess with exponents for a while, and then we're going to get into logs. You guys learned logs last year. How do you feel about logs when I mention that right now? Are you like, yay, I love logs. Logs are great. Are you more like, I don't care about logs, or is it logs terrify me? Anybody in the last one? A lot of times my pre-calc students come in, they're like, oh, I hated logs last year. Logs are the worst. I never wrapped my head around it. And that's okay because that was like one of the few things that was brand new last year, right? Like brand new. We don't touch logs in Algebra 1 or in geometry, so it was so the nice thing is this year will be the second time you've seen them, and this is where things kind of click into place with logs, okay? So you're going to trust me on this, but if you guys will work with me, I think you're going to walk out of here feeling pretty decent about logs. And the thing about logs is that logs are just exponents. So if you know your exponent rules, then the log rules are just those things but in reverse. So if you can be really comfortable with these, my goal is to try and connect logs to exponents so that you can feel just as comfortable with logs. However, if these are a little bit shaky for you, that's going to make that connection difficult to make, okay? So again, you got like until next Tuesday before we start looking at logs. Sharpen up your exponent skills if you need to. But if you kind of felt pretty comfortable with most of these, then you should probably be in good shape. All right. No logs today, though. All exponents. We're going to just practice some stuff from Chapter 1. Graph and analyze. We love these in Chapter 1. This is that long list of stuff that we had to look at a graph and write everything down. Remember doing this? Well, we're going to do this over and over again this year. Just wait. Next semester it'll be with trig functions. Let's go ahead and do this basic exponential function. So let's fill out our table here. This should be pretty easy. I like starting with 0. 2 to the 0 is just 1. Anything to the 0 is 1. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. 2 to the negative 1 just moves that 2 down to the bottom. 2 to the negative 2 is 2 squared, but on the bottom. That's 2 to the third, but on the bottom. All right, let's graph this thing. Let's graph it. So this is our, we'll kind of think of this as a version of our parent function. All right. Let's practice our analysis skills. Where should we start? We got a lot of stuff we can analyze. We did domain and range a bunch last time. Let's do domain and range. What's the domain of an exponential function? Everything. Anything can go into an exponent. As long as your base is positive, and that's all we're going to be dealing with in this class. If you have a positive base, no matter what your base is, your domain's going to be all real numbers. The range, not so much, though. This doesn't have any y values that are negative, and actually it's never going to hit the x-axis either. So the range is y is greater than 0, or we could say 0 to infinity. What else do we do on our list? Intercepts. Let's do intercepts. So we want x and y intercepts. I see a y-intercept at 0, 1. Are there any x-intercepts? No. Intercepts. We did rational functions recently. Those had asymptotes. Do exponential functions have asymptotes? Uh-huh. Uh-huh. There is a horizontal asymptote. That would be y equals 0. So our asymptotes, there's only one. It's y equals 0. What else was on our list? What else do you guys remember talking about back in chapter 1? Oh, there were a whole bunch of things. All right. I heard bounded. Is this bounded? Above, below, both? Bounded below? Okay. I heard increasing, decreasing. This is, I think it's always increasing, isn't it? It seems to flatten out, but it's still, as we move to the right, it's always going to be increasing. So I would write this as increasing over all real numbers, which means it's never decreasing. Someone said continuous a minute ago. Is this continuous? Yes, indeed. What else? End behavior. I'm going to do that at the end. Extrema, yes. And on the CWU exam, because they use a different textbook, they're not going to call them extrema. Remind me what they're going to call them? Turning points. Are there any turning points on this graph? Nope. No extrema, no turning points. No local maxes or mins. What else before end behavior? Symmetry. Is there any symmetry about the about the y-axis or about the origin? Nope. And if there's no symmetry, that tells us something about odd and even. It's neither, right? It's not odd. It's not even. I think that's everything except for end behavior. Now, before you write down the end behavior, look at the left-hand side, and we'll make this multiple choice. On the left, is the graph going up, down, or leveling off? Up, down, or leveling off? Leveling off. And on the right, it's going up. That's kind of weird. Usually, if it was leveling off on one side, most of our functions were leveling off on the other side too, but not exponential functions. So when we write our limit notation, on the left, it's gonna level off to 0. On the right-hand side, it's going to infinity. So go ahead and see if you can remember what that notation looks like. I'm sure you can. You just wrote it 6 times on your test on Monday. Still working on those, by the way. I'm hoping to have them done by Friday. All right, any questions about what we've done so far? Let's go ahead and fill out the table for this next one, but we'll skip the rest of it. I feel like we've got a good review just now of all that. And you'll be analyzing some of these in your assignments too. What's going to change when it's a half instead of 1? These y values are actually going to be the exact same values. They'll just be backwards, right? So a half to the 0th power is still 1. A half to the 1st power is a half. Square it, you get a 4th. Cube it, you get an 8th. But negative powers, when your base is less than 1, are actually going to get bigger. So your graph's going to look very similar. It's just going to be decreasing instead of increasing. We won't take the time to go through and do the analysis. A lot of it's going to be the same, just reversed. All right. Here's another blast from the past. Transformations! Yay! I told you these were never going to go away. Transformations. We're going to transform a parent function of 3 to the x power into this. Let's start by counting. How many transformations are we going to have to fit in this tiny little space? To go from this to this, how many transformations do you see? I'm seeing 3 also, because I think of this negative and this 2 as 2 separate things. Is that what you guys thinking that too? The nice thing I like about this is I've got 2 vertical transformations, but they're both multiplying. There's no adding or subtracting. So we can do those in any order we want. And there's only 1 horizontal transformation, so we can do that in any order we want to. So order does not matter for this at all. You can do those 3 transformations in any order you want, and you're still going to get the exact same thing. Okay, because the reason is we're not combining any multiplication transformations with any adding or subtracting in the same direction. I've got a horizontal shift, but all the other stuff is vertical. So it's when you've got a horizontal shift and a horizontal stretch where you got to worry about order, or if I have a vertical shift and a vertical stretch. But we don't. So cool. We can start wherever. So here's my parent function, 3 to the x. We're going to track these things with x and y coordinates because that's how we always do these. If you had to guess the 3 x coordinates I'm going to ask you to track, what would you guess? 0 is one of them. -1 and +1 also. So plugging those in are going to give us 1/3, 1, and 3. And since this has an asymptote, we should also track our asymptote. So the horizontal asymptote will be y equals 0. Bless you. Every exponential function is going to have that asymptote at y equals 0. So we got our choice on what we're going to do first. What do you guys want to do first? The negative, the 2, or the +4? Negative first? Okay. So we'll stick a negative onto our function. And we'll describe what that's doing. That's a reflection over one of the axes, x or y, over the x-axis. And will that change our x-coordinates or change our y-coordinates? If I'm reflecting over the x-axis, it feels like my y-coordinates are going to change, right? So the x-coordinates will stay the same, and all the y values, including this 0, because that's a y value, have to be multiplied by -1. So we'll end up flipping signs on all our y-coordinates here. 0 times -1 is still 0, so that actually didn't change at all, did it? Do you guys need someone? I guess not. All right, we still got to do the 2 and the +4. Which one next? 2. All right. So this is a 2 being multiplied on the outside. That's outside, so that's vertical stretch or shrink. Vertical stretch by 2. Vertical stretch is going to change my x or my y coordinates. Y coordinates are going to change. So x's stay the same. They're getting kind of bored here. All my y values are going to be multiplied by 2. Including this 0. But that didn't change anything. All right, we only have one more transformation to do. That's going to be our shift. We're adding on to the x. It's backwards, so that's actually going to shift us left 2, or 4, left 4. Shift left 4. Which this time is going to change our x coordinates. We'll subtract 4 from each of our x coordinates. All my y values stay the same. So here's my asymptote, y equals 0, -5, 2/3, -5, -2, -4, -2, -3, -6. All right, there we are, reflected, stretched, and shifted. All right, how are we feeling? Was that enough to kind of remind us about all the transformations and the graphing and everything? So maybe we'll skip part of the next example, but I want to pause just for a second. Anybody have any questions on that? We're transforming pros by now, right? We've been doing this for a while. All right, flip the page again. I'm sorry that everything's upside down here, but I don't know what happened. So I don't want to skip the whole problem here because there is something that I want to at least get us started on with this. When you look at this function and we think in terms of transformations, I don't like the way that looks. Do you guys like the way this looks? What do you think? If I were doing this problem, I would probably start by rewriting my function with the negative x and a plus 3 like that. That looks nicer to me. It's the same thing, right? When I look at this, I can tell that I've got a reflection over the y-axis and some kind of shift. In fact, those are the only two transformations, right? I might actually change this one more time. Let's talk about we're not going to graph the points. If I wanted to get this, if I started with 2 to the x and I wanted to get this, what would you do first to come up with this? Would you do the reflection first or the shift first? You do the reflection first. So you would go from 2 to the x to 2 to the negative x. So you pull the x out and replace it with the negative x. And this would be a reflection over the y-axis. Agreed? Okay. And then what? How am I going to get that plus 3 on there? Add 3? We can't just add 3. Remember, with anything horizontal, we have to pull the x out, do something to it, and then replace the x with that thing. So I'm going to have to actually replace, if I'm trying to get this, I'm going to actually have to replace it with x minus 3. Right? When we're doing anything on the inside of the function, we actually remove the x, stick a parentheses where it is, and then whatever we do to the x goes inside of that parentheses. And if I want this to be a plus 3, because I got a negative on the outside, this is going to have to be a minus 3 in here. So this is actually, since we chose to reflect first, we're actually going to have to shift to the right by 3, which is not what I was expecting when I first looked at this equation. Okay. So if I wanted to get it into this format first, I'd actually want to probably do the shift left by 3 first and then reflect it over the x-axis. So when I told you a minute ago, I said I might, if I were doing this problem, I actually would not be dealing with this format. I would have looked at this and said, I remember there's a rule that says I can always shift last if the x is being added or subtracted inside of a set of parentheses. So I would have factored this negative out from the beginning. I would have factored that negative out and then thought of this as a minus 3. And then we could have just gone this path here to get to that final answer, instead of having to kind of think backwards about it. So my hint to you is, if you're working one of these problems, if there's a coefficient on the x, and you're adding or subtracting something, factor that coefficient out, and then you can shift last. Okay, I'm going to put another example up here. Let's say you're doing a problem in your assignment, and it's got 5 to the negative 2x plus 10. I would modify that and rewrite that as 5 to the negative 2, and then quantity x, what? Minus 5. Because if we can put it into this format, where x is being added or subtracted by itself without any coefficients, then the rule, if you can get into a format that looks like this, is shift last. Once we start graphing trigonometric functions in chapter 4, when you come back and look at this again, you're going to be like, oh yeah, obviously we want this coefficient in front. Okay. Maybe not so obvious to you now, but just practice that for now anyways. Okay, any questions on that? We're not going to go through and track them because I feel like you guys have done that a million times and we're good to go on that. Okay, let's talk about our general form for an exponential function. We got 2 parameters. A is going to be a starting value, or a y-intercept. If we're dealing with actual situation, the starting value would be like, how much money did I start off with in my bank account? Or how many people live in the state right now? How many fish are in the pond at the beginning? And then B we think of as a multiplier. It's whatever we're multiplying by over and over and over and over again as we move forward. So we're going to practice writing some equations. Sometimes the equations can be very simple. Sometimes we've got to do a little bit of work. We'll look at a little bit of both flavors here. So look at this first table. Can you identify the y-intercept in this first table? What is the y-intercept? Heck yeah, it's 5. That's our y-intercept, which means for this function, a is 5. And then the multiplier, now the multiplier is the multiplier that you would multiply the y by to go forward 1 in the x column. So this table is set up so that we're going forward. Each x is only going up by 1. So my multiplier, whatever I'm multiplying a 5 by to get 20, we should be multiplying by the same number to get to 80, and then by the same number to get to 320. And that multiplier is 4. We're multiplying by 4 each time we move forward here. So that tells us that b is 4. So knowing that, then we can write our equation. Y equals, we just need those two things. It would be 5 times 4 to the x power. And that's it. So if you got a table like this where the x values are going up by 1, oh, it's so easy and nice to write an equation. Can you guys spot an a or a b value on this graph on the second problem? You spot the a value. What's the a value? 1.5. Yeah, it's our y-intercept. A is the y-intercept, so we know that a is 1.5. And then when you look at the coordinates of the points, notice that the x value is increasing by 1. So we should be able to just figure out a multiplier to get us from that 1.5 to 3, and that should give us our b value. What do you multiply a 1.5 by to get 3? Good, so b is 2. So there we go. Y equals 1.5 times 2 to the x. By the way, sometimes when your book writes answers, they're always going to, not always, sometimes they will put the b value in parentheses. If b is ever a fraction, it must go in parentheses. But if it's not a fraction, you can just write it with a dot in between. All right, how about the third one? Can you spot an a value on this graph? A is 10. Nice. And b is 4/5. Oh, you would multiply a 10 times 4 over 5 to get to 6? Is that where you got that from? Oh, to get to 8. Where'd the 8 come from? Ooh, I think I know. I think I see. I'm going to make this into a table to make this easier for me to see. So 0, 1, 2. I know that we have 0, 10, and we have 2, 6. Is this where you were thinking the 8 would be? If this was a linear function, that would be an 8. If it was a linear function. But this is exponential. We can see that telltale curve in it. So I don't think this is going to be 8, but I love where you're going with that. Help me out here. How are we going to find it? What do you think? We could find what 2b is equal to. Oh, I like that. Can you go ahead and do that? I'm going to do it a different way, but I want to see if you come up with the same. Same answer. I bet you will. Would it be 2b? I don't think that's going to work, actually. Move that 2. Find b squared. Do what you were thinking a second ago, but don't put a 2b there. Put a t squared there instead. All right. We'll come back and we'll look at that solution in a minute, but I want to remind you guys of something. This is a super, super common thing that comes up in math, comes up all over the place in pre-calc, and it's going to come up all over the place in calculus also. So can you guys go ahead and, in this space here, write kind of small, write down y equals a times b to the x. Well, that's what we're trying to write, correct? That's the equation we're trying to write. And to finish this problem, all we need to do is find a value for a and a value for b. Agreed? We have one of those numbers. Could you please substitute one of those numbers into that equation? Write small. We're going to need some space underneath this. We know that a is 10. That puts us in a situation where I have an equation and I almost have every value I need for that equation. I'm just missing one thing. We've seen this before. This has happened to us before. This happened to us when we were trying to write the equation of a parabola and we were missing the a value that was out in front. Do you guys remember that? This happened to us in the situation where we were trying to write the equation of a polynomial. We didn't know what that coefficient in front was. Do you guys remember that? And then, I don't know if we did the rational functions, but it'd be the same thing to find the coefficient for the rational function. We did. We had to solve it. Do you guys remember how we found that value each time? We plugged in a point. That's the key, right? We do have a couple points here that we could plug in for x and y, and that would leave us an equation that we could solve for b. Okay? So let's do that. Let's plug in, now I'm going to say let's not use the 0 and the 10 since I already used the 10 here. Usually you don't want to use the same point twice. So use the 2 and the 6. Plug in this x and this y value. And let's see if we can use that to solve for b. So y is 6. 10 times b to the second. And then we'll divide by 10 on both sides. And then we'll take a square root on both sides. Andrew, did yours work out? Okay. Well, I want to go back and talk about your method in a second here. And I want you to keep that in mind when we do our last example here too. Six over 10. And we're not going to leave that like that. You guys know better than that. We're serious math students. We could simplify that, and that has a square root in the bottom of a fraction. We got two things to fix here. So I'm going to do some work off to the side here. This is the square root of 6 over 10 would be the same as the square root of 3 over 5. So I simplified the fraction. And I'm thinking that is the square root of 3 over the square root of 5. We're not allowed to have fractions inside of radicals, and we can't have radicals in the bottom of fractions. So how am I going to get rid of this square root on the bottom here? Fancy one! Yeah, I feel like we might have even maybe done this exact same one at the beginning. Is it the same thing? Totally! Oh, I flipped it upside down though, didn't I? So what would that give us? 15, root 15 on the top, plain old 5 on the bottom. There we go. There's our b. All right, now we can write our final equation. We got b. Since that's a fraction, the parentheses are necessary for that one. And I was tempted there for a second to divide the 10 by the 5. And I was like, nah, I better not do that. Is that x there? All right. Question? Yeah, so when we take a square root on both sides, technically we should have done plus or minus, right? Is that what you're saying? Great question. Thank you for asking that. Yes, technically it should, but when we deal with exponential functions, one of the rules is that b has to be positive. So there is a negative version of a solution, but we're going to throw it out because it doesn't make sense for an exponential function. Yeah, we should probably write that down up here in our notes. B has to be greater than 0. A can be anything we want. B has to be greater than 0. Technically, b could be 0, but that would be a really boring function, wouldn't it? You just take whatever this number is and multiply it by 0 a bunch of times. That'd be a pretty boring function. Might as well just write y equals 0, right? Why don't we not want b to be negative? What happens if, like, say b is negative 2 and x ends up being a half? Now you're taking negative 2 to the half power. That's the square root of negative 2. Nah, that's imaginary. That's why we don't want b to be negative. So yeah, thank you for that question. We should have, when I took a square root on both sides, I need to keep in mind that it could be positive or negative, but we're throwing the negative out because of the context. All right, the question came up when I was asking you for strategy. I'm glad that you guys so quickly came to plugging in the coordinates of the point. That makes me happy. You're going to do that again and again. Before we came up with that, Andrew, you had suggested, and I think what your thought was, since there's 2 steps here, you were thinking of this as 2b. You said 2b originally, but we're actually multiplying by b each time. So if we were to do that as one big step, we'd be multiplying not by 2b, but by b squared. So we could have used that thought process and said, okay, I know it's going to take me b squared to get from here to here. What do I multiply a 10 by to get 6? That was that 3/5 that you guys had already, or was it 3/5 or 5/3? 3/5. Yeah, so we could say b to the second is 3/5. And then we could have solved from there. We would have gotten the same answer that we just did a second ago. All right. One more problem. This one, I like this one. This is us, guys. These are actual values from the U.S. Census Bureau for the city of Ferndale. In 2010, there was a population of about 11,500 people. That grew by 4,000 people in the 10 years between 2010 and 2020. You guys were born around 2010, right? So that's a pretty big jump in population in that amount of time. Who is one of those people? Who are my move-ins? I am. I'm a transplant. I wasn't here in 2010. Yeah, that's about right. That's about a third of us are new people, right? Isn't that interesting? All right, so our goal is, can we write an exponential function that models this growth and then use that to predict some future populations? Okay, so we're going to have to use some of these techniques that we've been talking about. We know we're going to write a function in the format y equals a times b to the x. And we've got some data. For a problem like this, especially when it involves years like 2010 and 2020, I like to create a table that has 3 columns and get my data into that table. I've got x and y as usual, but then I will also include a year column. So I've got data for 2010 and for and for 2020. The cool thing about exponential problems like this is that when you're writing your function, you get to choose what x looks like. Like, if I wanted to, I could make the year 2010 be an x value of 2010. If I wanted to, I could totally do that. Or I could make it be something nice and easy that would make my job a little bit easier. We would really like to see a particular x value appear in this table somewhere, right? If we had a 0 in here somewhere, then A would be super easy to find, agreed? So we can make year 0 be any year. We can make it be this year if we wanted to. I'm thinking since this is the earliest year they gave us data about, why don't we make this year 0? You guys okay with that? So if we made this year 0, then 2020 would be year 10. I want you to realize that that choice is totally arbitrary, though. I actually could have made this year 0, and then 2010 would have been year -10. Okay? No, it's just 10 years before year 0. So when we do make our model, we can go back in time. If they wanted to talk about the year 2000, the way we've set this up, we would use an x value of -10, because that's 10 years before year 0, right? All right. And then we're eventually going to find values for 2030 and 2040. So let's go ahead and populate our table here. And the way we have chosen to do our x, that would be year 20 and year 30. All right, what did they tell us? We've got a population of 11,415 at year 0 and 15,623 in year 10. So we're going to try and write ourselves an equation here. Since we have strategically picked an x value of 0 to appear in our table, that's going to make A pretty easy to find. So I'm going to go ahead and start building out my equation here. A is, it's 11,415. I don't have a B value yet. Do you think you know how we're going to find it, though? No, plug in a point. Now, should I use the 0 and the 11,415? Probably not, because we already used that once. You can try it if you want and see what happens. It'll be a little bit of a letdown. You won't get very far. I'm going to use the 10 and the 15,623. So 15,623 equals 11,415 times b to the 10th power. All right, and we're going to solve this. Now, some of you are going to have this super strong urge to reach for your calculator right now. Don't do it, okay? So from here on, for the rest of the year, when we solve application problems that involve like a real world situation, we're looking for a decimal answer, you only get to use your calculator one time at the very end when you solve, okay? We do not want to divide these things in our calculator, round off that answer, and then use that rounded answer to come up with another answer that we're going to round off, and then use that rounded answer to come up with a third answer that we're going to round off. Which you run into this thing called compounding errors when you do that. So what we're going to do instead is we're going to solve this thing until we get b by itself with fractions and radicals and everything, and then we'll type it into the calculator all at once, okay? So we're not typing this in. I am just going to write it. If I divide it on both sides by 11,415, we would just have this big old nasty fraction here, but that's okay. We know, we have faith our calculator is going to deal with this in a second. And that's equal to b to the 10th. And then one more step of algebra will get b by itself. What are we going to do to get rid of that 10th power? We'll do a 10th root. And now b is by itself. Now we're going to reach for our calculator and type that in. And let's stick with 4 decimal places. Let me show you how to do this in case you've forgotten. It's a 10th root, so you're going to type in the number 10 first. And then the math button. And you're looking for a radical that's got a little x on it. So this is what mine looks like. Some of yours are actually, they're going to tuck that little 10 up inside of the root. That's fine. When you do this, you need a parenthesis to tell the calculator that we want to keep the 15,623 together with the 11,415. You should be coming up with a value about 1.03. If we go 4 decimals, it'd be about 1.0319. So we have everything we need now to write our equation. I want to pause for questions. Please don't answer the rest of the questions yet. I want to show you a little trick here. If you've written down that equation, just pause right there. I want to pause for questions from you guys, and then I have a couple questions for you guys. Who's got questions for me? We feeling okay about this? All right, here's my question. Can somebody please tell me what percent is Ferndale's population growing by each year? By what percent? That was terrible grammar, by the way. I'll do better. By what percent is Ferndale's population growing each year? What do you think? About 3. If I want to be more exact, I'd say about 3.19. Right? Because if this is a percentage, would be 103.19. That tells us we're keeping 100% of the previous population plus another 3.19% on top of that. You guys remember doing that back in Algebra 1? So that gives us an idea of how much we're growing each year. It's only 3%. Only 3%. Okay, now we're going to actually type these in. I want to show you guys something awesome on these calculators. Actually, we've seen this already. Do you still have that number on your screen? You didn't clear it out yet, did you? If you did clear it out, you can just hit enter again and it'll come back. I want you to take that number and I want you to stow it. And I'm going to stow mine into the variable b. The stow button is on the left side of your calculator right above the on button. When you hit that stow button, it's going to say ANS. That means take the last answer you got, stow it into, and let's store it into b because that's what it is, right? The cool thing about these calculators is they'll save all these decimal places, but then there's like another 8 decimal places that it has in its memory that are stored. You can't even see. If you hit enter, it's just going to show you the same number again. But here's where this is useful. Now, when I go on to use my function here, I'm not using this rounded off version. Well, it is a rounded off version, but it's a much more precise version. So to figure out for year 20, to find year 20 over here, I need to stick 20 into this function. So I'm going to type in my calculator 11,415. Instead of typing in 1.0319, I'm just going to type in b. Because my calculator currently has a value for b that's like super precise, lots of decimal places. And then I'll put my exponent of 20 onto that. And that'll give me my population of about 21,382. And then if I wanted to know for what's going to happen at year 30, here's another fun calculator trick. If you don't want to type that whole thing in again, just hit second enter. It'll bring it back and allow you to edit it. Change your 20 into a 30 and you got your answer for the second question. I got news for you guys. By the time you're 30 years old, there's going to be 30,000 people living in this town. That's twice as many as we had in 2020. Question? 6-4, thank you. Usually, not always, some years about this time I'll get some questions about how do we round portions of people, and my answer to that is we're going to be respectful, number one, okay? So we're not going to make jokes about parts of people, okay? And just think about the context of it. Like, it depends on what you're, You know, you probably, if your job was to plan for how much housing we needed, we probably wouldn't just round that to like 29,000 or maybe 29,300 or something like that. Okay. All right. Other questions? We're super close. I got another big question for you. Is Ferndale actually going to keep growing exponentially? If you guys come back here 100 years from now, do you expect that there's going to be 263,000 people living here? If you come back here 200 years from now, do you expect that there are going to be 6 million people living in Ferndale? No, okay? Because it turns out exponential growth doesn't happen without bounds. Please don't miss this because you guys are responsible for learning about logistic functions. I'm going to tell you what a logistic function is. A logistic function starts out like an exponential function. It grows exponentially, but at a certain point, it levels off. Usually that's because there's just a limit to how much population, how much space there is for housing or something like that. Those of you who were paying attention 5 years ago might have heard on the news, level off the curve. Do you guys remember hearing that? We need to flatten the curve. When they were talking about COVID, they were talking about how COVID was growing exponentially and we needed to flatten the curve. This is what they were talking about. This is called a logistic function. Your responsibility is to spend about 5 to 10 minutes reading these 2 pages. I need you to know what the equation of a logistic function looks like and how can you find the 2 horizontal asymptotes. If you can come back and know those 2 things for me, that would be great. I am going to, as soon as the bell rings, go on to Canvas and modify the assignment. I'm going to cut some stuff out of the book assignment to make up for the fact that I'm asking you to do a little bit of self-study and that I'm adding on problem 2 from the optimization problems, okay? So I'm going to cut a few problems off of what's in the book. If you've already written it down, make sure you go back and check Canvas before you get started on it. Of course, you're welcome to do more problems than I assign to, always, okay? Thank you guys for your attention. Thanks for putting the chairs up. That's super helpful.